Good afternoon, everyone. I am Chandra Devnath, one of the PMRFs of Pfizer Berhampur. I am pursuing my PhD in organic synthetic chemistry. I am the TA of this course named A Study Guide in Organic Retrosynthesis and Problem Solving Approach. In our previous classes, I have already discussed about some important name reactions and some important organic reactions and their applications, which may help you to plan any retrosynthesis of any important compounds. So after that we are moving to the how to plan retrosynthesis of a new or unknown compound. So today we will solve some more questions based on that. So I have already discussed all these name reactions and some others of which have not been mentioned in this list. We have already discussed. We have also discussed some olefination reaction and some reactions of olefins. Then we move to some reactions where we do not need any kind of reagents like the thermal and photocatalytic reactions. Now the topic we are discussing, that is what is retrosynthesis and some retrosynthesis of some important molecules. So this is one of the questions. So how the relationship between two carbonyl group in here I have given three compounds. Here you can see they are just one carbon apart. That these two carbonyl compounds are one carbon apart. In this case, this is 2 carbon apart, and here it is 3 carbon apart. So how will you plan the retrosynthesis of these 3 compounds? So let's do one by one. So if we just disconnect from at this place. We know alpha position with respect to carbonyl is electronegative. So these are the synthons of this compound. So which will be the synthetic equivalents? These are synthons. These are synthetic equivalent. So what will be the forward synthesis? So this negative charge can be generated in a two pathway. The negative charge at the alpha position can be done in two ways. One is simple LDA by using lithium diisopropyl amine. Another is enamine synthesis. Sorry, it's not enamine, it's from by I forgot the name. Anyway, if you can go through by this of enamine synthesis, we just add this pyrrolidine. It will combine with this one and form this imine. After that, if you add immunity, this base will take a proton from here. In the next step, if we add this electrophile, we add this electrophile. We add this electrophile, it will be incorporated in the similar way. So whenever there is two carbonyl at one carbon apart, you can go through this disconnection pathway. What will happen in this case? When two carbonyls are two carbon apart, then if you just disconnect from at this place, So forward synthesis you can plan easily in the similar way. If you add LDA and if you add this electrophile, if you add LDA and followed by this kind of electrophile, then you will get this carbonyl with 2 carbon apart. What will happen in this case? Just think, I just give 2 seconds, just think about it. When this is 3 carbon apart, obviously the cut will be from the alpha position of the cyclopentanone ring. Now the thing is, you have to change the electrophile in such a way that you will get 3 carbon apart. Whenever this is 1 carbon apart, we choose simple ester. When it is 2 carbon apart, we chose the alpha bromoketone. When this is 3 carbon apart, the electrophile will change. So in this case, now in this case, as the nucleophile is attacking to the beta carbon of the alpha beta unsaturated compound, so beta carbon electrophilicity is not that much high than compared to the carbonyl compound. So in that case, the nucleophile should be reactive enough so that the reaction takes place. So that you have to make the nucleophile strong enough. In this case, as our synthetic equivalent, instead of simple cyclopentanone, we can use this. Because in this case, the negative charge generated at this place, this proton is highly acidic because of 2 carbonyl compounds. This proton becomes highly acidic and the nucleophile becomes highly reactive. So if you draw the forward synthesis, in the next step, So it will form this kind of compound. Now if you just add acid and some amount of heat, this CO2, this ester group will be hydrolyzed to CO2H carboxylic group, and after that while heating it will be removed as a carbon dioxide, and we will get our desired compound. We have to plan the retrosynthesis of these natural compounds. Whichever reagents we require in the question mark we have to mention. To see the question, let's attempt this one by one. Suggest the synthesis of the starting material. So this is our starting material. You have to suggest the synthesis of the starting material. Suggest the reaction for each step. Draw the retrosynthetic analysis giving the this connection. Which synthon does the starting material represent? So this question is not that much. Let's cut this one. This is not required. We'll just attempt these three. So first, suggest the synthesis of the starting material. So if you see the starting material, to know the synthesis of the starting material, we have to do the retrosynthesis of the starting material. This is the retrosynthesis of the starting material. This is in this way. If you add HBr to this alpha beta unsaturated aldehyde, H will be added here because it will go through a electrophilic pathway. It will take a proton from this step and the positive charge will be created here, and Br minus will attack at this place. So it will give us this beta bromo compound. After that, if you perform the Grignard preparation reaction by using magnesium and ether, you will get this Grignard as our product. Sorry, first you have to protect the aldehyde group. First you have to protect the aldehyde group by ethylene glycol. In the second step, if you add magnesium and ether, the Grignard will be created. Okay, so this is how starting this one can be prepared. The next step is suggest the reagent for each step. So to get an idea about the reagent, we have to get a retrosynthesis of this compound. So this is the retrosynthesis of this compound. If you just cut from this place, as aldol reaction can give us this compound. So if there can be an aldehyde. Next, if you do functional group interconversion and add a OH at this place, Then if you cut it from this place, it can be a carbonyl and the negative charge can be created here. So let's see the reagents required one by one. So in the first step, there is a negative charge here because of Grignard compound. So it has been, this part has been incorporated. Okay, so if you add, I'm just mentioning as A, B, C. So what will be our A? A is this aldehyde, ketone. You take this ketone and add to this Grignard. The Grignard will attack to this keto center. The Grignard, you take this Grignard, I'm just drawing as RMGB here. This Grignard will attack here and it will open up and give us this as our product. In the next step, they just remove the OH group. So just to remove the OH group, what we can do? So in this one, if you add H plus, if you add H plus, this OH will be removed and a double bond will be created here, and this aldol protection group will be deprotected. So we will get this type of compound. In the next step, if you add a reducing agent, the double bond will be reduced to give us this. This double bond will be reduced and we will get this single bond compound. So what is our B? So B is a combination of two reagents. The first step, we have to add H plus, and in the second step, what we need? We need a reducing agent. In the next step, this group has been added. So you just perform Wittig of this compound. If you just perform Wittig of this compound by using a specific Wittig, we can get this product. So you can perform Wittig of this compound by using take this Wittig as a reagent and perform Wittig of this carbonyl compound, we can get this as our product. Okay. So we have answered all the questions. So we have suggest the synthesis of the starting material, the reagents required we have all, and the third one we have already answered, the retrosynthesis we have done already. Okay. Draw the mechanism. So we have to draw the mechanism to get this product from this substrate by using this as our reagent. So so they have given H plus to go through a enolization. So if you add H plus, whenever this is base catalyzed enolization, it take up a proton which is more acidic. But whenever it is acid catalyzed enolization, it will take a proton where after formation of enol, which will give the more substituted double bond. So if it is acid base catalyzed, it will take the more acidic proton. So here which proton is more acidic? There is a proton here and here. So obviously this one is more acidic. This one is more acidic because, and this one is less acidic because of plus I effect of these alkyl groups. So when it is base catalyst, it will take up this proton. But here they have mentioned we have to do a acid catalyzed reaction. So obviously it will take a proton from here because after the ionization the double bond formed here, which is more substituted double bond. So we add H plus. The next step, so we'll get our desired product. Have to plan the retrosynthesis of this one. Just cut from this place. This how to plan a retrosynthesis on which bond to be clipped is from experience. How much as much as problem you will solve, you will get an idea. As this is 3 carbon apart, so we know that what will be our electrophile. We've already done it. Whenever this is 3 carbon apart, the electrophile is a alpha beta unsaturated compound. So this is our starting material. So do you know what is the reaction? Actually, the reaction is a Robinson annulation reaction. This, if you draw the forward synthesis of this one, starting from the cyclopentanone and this alpha beta unsaturated compound, it is actually a Michael addition. You see, this step is Michael addition, and this step is aldol reaction. So Michael followed by aldol is Robinson annulation. This is the product of Robinson annulation, which you have already been discussed. Draw the mechanism of this compound from the starting material. So if you add methoxide and methanol, it will take a proton. It will take a proton from here, and that will attack to this alpha chloroester and chlorine. No, actually this reaction will go through. Now see, in your reaction medium, both have been added. In your reaction medium, this acetone has been added and also this chloroester. Now if you add base, it will take a proton from the place where it is more acidic between these two substrates, because both have been added at the same vessel. So between this hydrogen and this one, which one is more acidic? Obviously this one, because it has a ester group as well as a chlorine. So minus I effect of chlorine and also the minus R effect of CO2Me. This hydrogen is more acidic. This hydrogen is more acidic. Because of that, it will take a proton from here and generate Now if you add acetone, it will give us this O minus. The next step, as chlorine is still there, so it can attack here and remove the chlorine. Draw the synthetic pathway from this to starting material to this. So from here you can see, if you cut from this place, this part is coming from this acyl chloride. Okay. The rest of the part we have to synthesize, because we have just given as a benzene. So this amine we have to incorporate. So if you just undergoes nitration reaction, because amine cannot be incorporated directly. We can enter the NO2 group, and if you reduce it, you can transfer to amine. So if you add perform the nitration reaction, This reaction or simplest reaction. If you add this mixture of H2SO4 and HNO3, it will undergo the nitration reaction. In the next step, we just reduce the NO2 group.
Hello, ma'am. Hi.
Yes.
Hello. After aniline, we add CH3, CH2, no?
Yes, ethyl iodide.
Ethylia propyl.
So,
So structure
sorry, it is.
correct.
Sorry, it will be ethyl iodide. Okay. In this way, we can prepare this compound. Okay. So design the synthetic pathway of this one. So if you just cut this one, what we get? A pH with a negative center, with a negative charge, and a CO with a positive charge. First, you have to cut this, because in our starting material this part is not here, this part is not there. So if you just cut this one first, so we are getting this pH there will be a negative charge, and there is a positive charge here. Now what will be the synthetic equivalent of this one? The equivalent of this one, if we add just a bromine, allyl bromide you can use in this case. For this one, now we have this, because by using just LDA and diethyl ether we can generate a negative charge at this place because of enolization, and it can attack to our vinyl allyl bromide. Now the next is how we can prepare this from this simple bromobenzene and this aldehyde. So if we just cut from this place, so we have bromobenzene. So this can be prepared from phenyl magnesium bromide, because in that case phenyl become negatively charged. I am doing a step jump. After this cut, phenyl will get a negative charge and this part will get a positive charge. As phenyl is getting a negative charge, so that means it's a Grignard. So, and Grignard can be prepared from bromobenzene. So I just did a step jump because we have done lots of reaction like this. And at this step we can use simple some acyl chloride. So if we perform a we have to prepare this from aldehyde. So before cutting this one, we can do a, because we need, if you have started from acyl chloride, then we just perform the reaction on one step, acyl chloride and phenyl magnesium bromide. But here they have mentioned the starting metal is a aldehyde, so we have to do a functional group interconversion so that we can start from aldehyde. So if we do a functional group interconversion and make this carbonyl as OH, next step, if you cut this one, we'll get this phenyl magnesium bromide, and this aldehyde. Phenyl magnesium bromide can be prepared from PHBr and so magnesium. So if we draw the forward synthesis of this one, I'm just drawing the reagents one by one. I'm just writing the reagents one by one. Forward mechanism you guys try by yourself so that it will give a clear idea. So first we have to add magnesium ether Then in this way you can prepare the Grignard. Then it will attack to the aldehyde, give us a alcohol. Then we have to oxidize this alcohol. For that one we need a oxidizing agent like PCC. Ether, the role of ether here is just a solvent. The role of DCM is just as a solvent, because we need some solvent to mix the starting materials. It will be oxidized. In the next step, if you add LDA, then this proton is acidic. It will undergo the enolization, and that enol will attack to this vinyl bromide. So if you add usually this LDA reaction usually perform at low temperature. So it will take a proton, and if you add the vinyl bromide, it will attack to this, and we will get our desired compound. The product after each step, just try to draw by yourself, you will get a clear idea. So this is our forward synthesis. This is our forward synthesis. This is our forward. So after this we will get our target molecule. We will get our target molecule. Draw the synthetic pathway of this one. So they have started from aldehyde and this bromobenzene. So this part is new. So if I try to draw the forward synthesis directly, let's try once. If you can draw the forward synthesis directly, then it will be, that means you have an idea of retrosynthesis. So as you have done in the previous, we have to incorporate this phenyl to this carbonyl compound. For that we have to make this bromobenzene nucleophilic. And how we can make a bromobenzene nucleophilic? By transforming it into a Grignard. So if you just transfer it into a Grignard, reagent, we know that phenyl, magnesium and ether. We have transferred it into a Grignard. After that, if we add this aldehyde, followed by oxidation of the OH group. Now there is a NO2 at this meta position. Now if you perform a nitration reaction, as this carbonyl group is electron withdrawing, it is a meta orienting group. So in presence of this carbonyl compound, the incoming NO2 will enter to the meta position. It's a meta orienting group. Sorry, meta directing group. What is orienting? It is a meta directing group, because we have Fidelkraft similar to the Fidelkraft alkylation. This we have studied in our basic, I think. Whenever there is a electron donating group, in that case, when we perform an electrophilic substitution reaction on a benzene ring, the incoming electrophile enters to the ortho and para position. That's why the electron donating groups are called ortho para directing. Whenever the functional group is electron withdrawing, then during the electrophilic substitution on the benzene ring, the incoming electrophile enters to the meta position. That's why the electron withdrawing groups are called meta reacting. Why they enters to the orthopara and why meta? For that you have to go to study the electrophilic substitution for aromatic compounds. Electrophilic substitution for aromatic compounds. This is in Claydon. It's explained in a proper way. You can go and check for the electrophilic substitution for aromatic compounds. So the ketone is a meta-directing group. So if you perform the nitration reaction by using HNO3 and H2SO4, then the incoming NO2 group will enter to the meta position. In the next step, we have to enter this PHCO group. So if we add simple LDL, which can perform the enolization, followed by benzyl chloride, followed by benzyl chloride, it will give us our target molecule. You can try the retrosynthesis of this compound by yourself. If you design the retrosynthetic pathway. So what is toluene? Toluene means a benzene ring with a methyl group. This is called toluene. Now see what are the changes in the substrate and product. So there is a benzyl bromide group and a toluene. So toluene part is here, we can see. Now the benzyl bromide group, there is a benzene ring here. One carbon, if you consider this, there are 2 carbon has been extended. Two carbons has been extended. So we have to incorporate this group at the ortho position of the toluene. How is this possible? So if you try the retrosynthesis, let's cut from here first because we need to disconnect this benzyl bromide part. So if you cut from here, get a CH3 group here, and so this is a 2-methyl acetophenone kind of compound we'll get, and there is a benzyl bromide as possible. In the next step, so toluene we already have, we have to incorporate this keto group. Now we know that toluene is a methyl is a electron donating group as a because of its plus I effect, that is the inductive effect. So toluene methyl is a orthopara directing group. Methyl is a orthopara directing group. So the incoming electrophile will enter to the ortho and para position. Now between ortho and para, the para position is always favorable over ortho. Sorry, I pressed something. The para position is always favorable over ortho because of steric hindrance at this ortho position. So ortho position suffers from huge steric hindrance. The ortho positions are not that much favorable. But if your para position is blocked, then there is no such option. Then the incoming electrophile will always enter to the ortho position. So for this one, if you keep this, if you want to perform the electrophilic substitution of the toluene and incorporate this acetone group, this keto group, in that case this para position is available, so it will enter to the para position, not to the ortho, so you have to block the para position. For that one, if we perform a sulfolination of this compound, then it will enter to this para position. In the next step, if we add this acetyl chloride, then there is no such option with respect to the until unless the ortho position. We know why you use Sl chloride, aluminum chloride, just to enhance the electrophilicity of this compound. So this chlorine has a lone pair, so it will give this chlorine to this Lewis acid, that is aluminum. Then therefore the positive chlorine become positively charged. Because of that, it is this carbon chlorine bond breaks very easily, and this positive electrophilicity of this center enhanced. So we will get the next step. Now we have to remove the SO3H group because the purpose is done, and in your target molecule there is no SO3H group. So if you just add water and heat it, it removes from the system as a sulfuric acid. Now in the next step, we have to incorporate this benzyl bromide group. So if you just add LDA, because we have to because there is only one H is available, there is no such other option, so it will take a proton from here only. So if you perform LDA followed by benzyl bromide, it will incorporate at this center and will give us our target molecule. Okay. Design the synthetic pathway. So these are the small ones. You can do it by yourself. So I am just showing one. So this is a compound. So if you just cut this part, then there can be a positive charge here, and methyl can take a negative charge. So this positive charge can be compensated if you just see, it can be an aldehyde, sorry, a ketone. And this methyl can be negatively charged. Methyl can be, whenever there is alkyl group or aryl group with a negative charge, that we can get from Grignard. Just think about Grignard. So methyl magnesium bromide we can use. So similarly, this one can be also generated from this ketone. So there can be two pathways. One is if you just disconnect this ethyl group, then it can generate from this phenyl ethyl ketone. So ethyl phenyl ketone and ethyl magnesium bromide. There is another probability. There is another probability, that is, if you cut the phenyl group, if you cut this phenyl group, then it can be generated from diethyl ketone and phenyl magnesium bromide. As the substrates are not mentioned, so we are drawing both the retrosynthesis. What will be the product here? What will be the retrosynthesis of this compound? Just cut it from this place. So it can be a Wittig reaction between this acetone this Wittig salt. If we perform the Wittig reaction between these two, we can get this as our product. Design the synthetic pathway. For that one, we just cut one of the double bond.
ম্যাম
Yes.
লাস্ট ওয়ান ওটা তো আমরা দিয়েও করতে পারতাম, গ্রিগনার রিয়েজেন্ট দিয়েও করতে পারতাম। PHCH2MgBr.
We can do that. For that one, you have to use this acetone and then Grignard. But by this way, that is also possible. Actually, retrosynthesis can be in a various pathway, whatever you want to design, whichever is favorable based on the reaction condition. We usually do that. If you take the Grignard, then you have to prepare the benzyl magnesium bromide. You have to take the benzyl magnesium bromide, not even the benzyl magnesium bromide, it is be 2 carbon apart. Then that magnesium bromide will attack to the acetone, then we will get this one. Retrosynthesis can be in a different way also. So for this one, if you cut one of the double bond, then you have to enter one. If you do a functional group interconversion, then you can incorporate a OH group here. In the next step, you cut this bond also. It gives a positive charge here. And a negative charge here. This can be a aldehyde. For this one, now we know that to make this hydrogen acidic, we need a double bond at this place. Otherwise, this hydrogen is can't be acidic enough to be taken up. So, if we draw a structure like this, this is a imine structure. Now if we draw the forward synthesis of this one, so you can start from this ketone. If you add this pyrrolidine and H plus, it will form this imine structure. In the next step, if we add benzaldehyde and NaOH, NaOH is a base. We add benzaldehyde and NaOH is a base. So this proton is acidic now because of resonance conjugation with this imine center, because it go through a enamine formation. So this hydrogen become acidic. So it will goes to this, and through imine formation it will give us this alcohol, because it will attack the aldehyde group and will open up and give us alcohol and a imine here. Now in the next step, we have seen this imine is as a amine form, so you have to reduce the imine. So if you perform a reduction, LiLH4, LiLH4 can reduce imine to amine. In the next step, now we have to remove this OH group and form a double bond here. Now the thing is, so if you just remove this water molecule, so dehydration will get our target molecule. For removal of this OH group, we can transfer it to a good leaving group like TMSCl. If you use TMSCl, it will be a OTMS, then it can be removed easily. We don't need harsh condition, because if you give harsh condition, this amine bond can also be affected. So if you add TMSCl, it will be transferred to OTMS, which is a good leaving group, then it will be removed very easily. Provide the retrosynthetic analysis of these two compounds. So I can prepare this. So there is a cyclohexane. We know that in case of Diels-Alder reaction, always a cyclohexane ring forms. So we can plan this reaction by using Diels-Alder in one of the steps. That is, whenever there is a cyclohexane ring with a double bond, we can plan the reaction by using a Diels-Alder reaction. Now I have to plan how we can break the bonds. Okay, so if you just do a functional group interconversion, and this OH groups becomes acids, because we can easily hydrolyze the acid groups to OH. So that's why we are doing this functional group interconversion. Now if we just break the bonds from here, like Diels-Alder reaction, if you do a retro-Diels-Alder reaction, then there are two bond formation always. So if you move the movement will be like this comes here, so the two components will be like kind of this. And another is so if we perform a Diels-Alder reaction between these two followed by a reduction, we can get this as our compound. Instead of acid, we also can use ester, which are easily available in market. You can use ester. So what will be the forward synthesis? If you have to, you just try by yourself. I am just writing it. The forward synthesis will be first. I am just writing the reagents of the forward synthesis. Just try by yourself. So what will be the reagents for forward synthesis? First, we have to perform the Diels-Alder reaction. Diels-Alder reaction, we do not need any reagents, just heat. Then if you just use this ester and this butadiene, you will get this compound where these two are ester. Now the ester can be hydrolyzed by using divalage. You use divalage. These two ester group can be easily hydrolyzed. easily reduced to 2 alcohol group. There is another probability if you are starting from acid, if you are not starting from ester, then for reduction instead of divalage we will use BH3SMA2. This is for ester hydrolysis. This is for ester reduction. Sorry, I am just saying hydrolysis. This is for ester hydrolysis. Whenever this is ester reduction, we are using divalage. But if you want to reduce the acid group, in that case we have to use BH3 SME2. These are the specific reducing reagent for some functional group we use in our laboratory. So for acid reduction we will use BH3 SME2, and if it is ester we will use divalage. So based on our preference we can start, or based on the ability of the starting material, whichever we have in our laboratory, or which we can do that way. If you have the acid one, we can start from acid with butadiene, we will get this compound and reduce by BH3SME2. If you start from ester, we will get the Diels-Alder compound, and we can reduce the ester group by using divalage. Now in this case we can also plan if you just break the bonds from here, then it can perform Diels-Alder reaction between these two. Now this is a 4+2 cycloaddition reaction. This is a 4+2 cycloaddition reaction. So 4+2 cycloaddition reaction means 6 pi electron, and it's going via heating condition. If you go through our photochemical reaction, you can go get an idea of that one. So if it is a 4+2 reaction and is performing under heating condition, so as it is both the CO2 mean at the same plane, so here in this case also both the CO2 mean should be at the same plane. And in this case the methyl group are opposite to each other, so that's why. Okay, so you have to perform. If you just how this electronic combination, for that one you have to see the photochemical the cycloaddition reaction or the pericyclic reaction rules, how the disrotatory and conrotatory takes place. That is a different topic actually, so due to the limitation of the time I cannot explain. You can go and check photochemical the cycloaddition reaction or the pericyclic reaction. In that, how based on the number of electron, like if it is 4n+2 system, it will go and it is a heating condition, it will be disrotatory or conrotatory. All these things are comes in this place. So based on that we have to determine the stereochemistry. For that one you have to read pericyclic, you can go and check. But for simplicity, yes, in the substrate both the CO2 mean in the above plane, that means in the substrate layer will be in the same plane, so they have drawn in the same plane. As this is in the above, is in the below, so if it is going outside, it will go to the inside because they are trans to each other. This is for simplicity, I am just drawing it like this way. So this is the last question. Design the retrosynthetic pathway of you cut from here, There is a positive charge and there is a positivity of positive charge can be compensated by this alpha beta unsaturated compound, and you can generate a negative charge here. So you can, if we cut from here, it will be CHO minus and there will be alpha beta unsaturated compound. And CHO minus can be generated from this aldehyde protected from which is called umpolam. Okay, so if we draw the forward synthesis, you will get the idea how what I am talking about. So first we will take this formaldehyde and perform a protection of this one by using ethylene glycol and H plus. So it will give us this protected aldehyde. Now due to umpolang effect, what is umpolang? Whenever there is a polarity reversal. So this aldehyde is always electrophilic. We know aldehydes are always electrophilic. But now due to minus I effect of this oxygen group, this hydrogen become acidic. So in presence of base, it can be easily taken up. If you add any base, it can be easily taken up, giving us this anion. This is called giving us this anion. So So this is called umpolang or ampolang, means the polarity reversal. Polarity reversal means the aldehyde was electrophilic in nature, but just using this pathway, we made aldehyde a nucleophilic center. That's why it's called a polarity reversal or a ampolang. Ampolang. Okay. So their polarity has been reversed because it was electrophilic in nature. Here it was electrophilic in nature. It was electrophilic in nature, but after the protection and base removing the hydrogen, it become nucleophilic. That's why it's called ampolang. In the next step, if you add this to alpha beta unsaturated aldehyde, it will attack to the beta carbon. It will attack to this beta carbon. In the next step, if we add LDA, it will take a proton from this alpha position of this aldehyde. In the next step, if we add LDA followed by another molecule of alpha beta unsaturated aldehyde, then this proton will be taken up and form a enolate, and this center will attack to this beta carbon. So we'll get attack to this beta carbon, giving us this long chain aldehyde. In the next step, we can see this has been reduced. So if you just reduce the, we are not deprotecting it yet, because if you just deprotect it if you perform the reduction after the deprotection, then there will be two aldehyde and both of them will be reduced. But here you can see this is as aldehyde, so we are not deprotecting it. We will perform the reduction first, then we will deprotect it. So we will perform the reduction. For aldehyde reduction we can use we just reduce it, and then we just deprotect it by using acid. Then we will get our target molecule. Okay, so thank you everyone. This much for today's class. So today we have been discussed different retrosynthesis of different type of compounds. So I hope it may help you to get an idea and to solve some questions for upcoming examinations. So thank you.